Hello viewers, welcome to today's lecture on multiplexing techniques. In this lecture, we shall discuss various issues of multiplexing. First, we shall discuss why multiplexing, why do you really need multiplexing. Then I shall introduce to you the basic concepts of multiplexing, and as we shall see, the multiplexing can be divided into two different types: frequency division multiplexing and time division multiplexing. And as we shall see, the frequency multiplexing technique has two different variations, the frequency division multiplexing and wavelength division multiplexing. And the other one, the time division multiplexing, again has two different types, synchronous and asynchronous, which we shall discuss in detail. And finally, we shall discuss about inverse time division multiplexing, which is also in use today. And on completion of this lecture, the students will be able to explain the need for multiplexing, they will be able to distinguish between multiplexing techniques, they will be able to explain the key features of frequency division multiplexing and time division multiplexing, they will be able to distinguish between synchronous and asynchronous time division multiplexing, and explain the concept of inverse TDM. Why multiplexing? The observation, it is based on several observations. First one is, you will observe, it has been found that most individual data communication devices typically require modest data rates. For example, when you are sending voice, the data requirement is only say 4 kilobits per second, and obviously 4 kilohertz, that is the bandwidth. Of course, whenever you convert into digital form, then it comes to 64 kilobits per second. Then of course, that one is also not very big, and similarly the data rate required, average data rate required is also not very high. On the other hand, the communication media usually have much higher bandwidth. For example, nowadays we can use coaxial cable, optical fiber, microwave link, they have several megabits per second, hundreds of megabits of bandwidth, and as a consequence the communication media provide you much higher bandwidth. On the other hand, the users, individual users have lesser data to send, and as a consequence the two communicating stations do not utilize the full capacity of a data link. That means, if you have got two users, like say user 1 and user 2, say 1 and 2, and they are linked by a communication link, maybe optical fiber, coaxial cable or whatever it may be, they are not able to utilize the link capacity fully. Another observation is that the higher the data rate, the most cost effective is the transmission facility. For example, if the data rate is small, then the cost per byte or per kilobyte is more, and if the capacity is large, say several gigabits, then the cost per byte or cost per kilobyte is much less. So, that means, if we use a link of higher capacity, then we get it as a much lower cost. So, that is the observation. So, based on this observation, it has been found that we can use a technique known as multiplexing. How we shall explain. When the bandwidth of a medium is greater than individual signals to be transmitted through a channel, a medium can be shared by more than one channel or signals by using multiplexing. Essentially, what you are trying to do, we are trying to share the channel capacity or bandwidth of a particular medium by several signals, by several users, and for efficiency the channel capacity can be shared among a number of communicating stations. That means, we have to utilize the channel fully, channel capacity fully, and for that purpose multiplexing can be done. And as you know, most common use of multiplexing is in long haul communication using coaxial cable, microwave and optical fiber. As you know, for long distance communication normally we use optical fiber or a terrestrial microwave or satellite microwave or optical fiber, and all these transmission media have high bandwidth, and these are to be shared by using multiplexing. I shall start with a very simple example. If in a telephone line which has bandwidth of only 2400 hertz, which is used for data transfer between two stations, and as you can see, we can divide it. If your data rate is small, which can be satisfied by say 1200 hertz, then you can divide it into two parts, say half 1200, so 600 to 1800, and another is 1800 to 3000. Then what can be done? The 1200 can be the first 1200 can be used to transfer data from say user A to B, that means in one direction, and the other one can be used for transfer of data between from user B to A. So, what you can do? You can achieve bidirectional data transfer with the help of a single channel, and only thing that we have to do, divide the bandwidth, and one part is used for one direction of data transfer, and that can be done by using multiplexing. For example, we can use frequency division multiplexing, FDM, or and in detail we shall discuss about it in more details later on. Let us see what is the basic concept of multiplexing. What we do, we use a device known as multiplexer, and which combines signals coming from n channels. Here you are getting signals from n channels 1, 2 up to n. Signals coming from n channels are combined together and sent through one medium. As you can see, you have got only one medium, and so n channels signals coming from n channels are combined to send through a single medium, and at the other end what we are doing, there is a demultiplexer, and the demultiplexer is performing the reverse operation. It is separating out the signals coming through a common channel and sending to n different channels, as you can see 1 to n. So, this is the basic operation. So, we require a multiplexer and a demultiplexer. So, this multiplexer and demultiplexer does the operation of combining and separating out, and it can be done in two ways. First one is known as frequency division multiplexing. Here, as you can see, the signals coming from n channels 1, 2 up to n channels are multiplexed, and they are sent simultaneously through a single channel. And so, as you can see, through the same medium we are sending n different signals, and obviously we are doing frequency division multiplexing. And frequency division multiplexing, as we shall see, the signals coming from different channels are translated, frequency translated to different frequencies, and that's how it is sent, as we shall discuss in detail. And at the other end, the demultiplexer will receive the signals, and then they will separate out the channels using suitable devices. So, here as you can see, all are sent in parallel. So far as time is concerned, if you look from the timing point of view, all these signals are combined to form a composite signal. So, here we are forming some kind of composite signal, and that composite signal is again demultiplexed at the other end by suitable technique, and as we shall see by using frequency division multiplexing. The second approach is time division multiplexing. Here, as you can see, the time is the signals are sent in such a way that in different time slots we are sending signal from channel 1, then we are sending signal from channel 2, then channel 3, and so on n, and this is being repeated. So, in time division multiplexing, signals are multiplexed in terms of time. So, for some time duration a particular signal is sent, then another signal is sent for another duration, then another signal is sent for another duration, and this way, as you can see as it is represented here. And at the other end the demultiplexer separates out signals for channel 1, channel 2 and so on. So, these are the basic approaches. Now, so far as the frequency division multiplexing is concerned, as we shall see, for frequency division multiplexing we use analog signaling. That means, we generate signal by using by using FDM and WDM technique, and it can, I mean, the analog signaling is used in two different techniques, FDM and WDM, and as we shall see, the time division multiplexing is done by using digital signaling, and that is why it is called TDM, and ATM stands for asynchronous time division multiplexing. So, we can say that analog signaling is used for frequency division and wavelength division multiplexing, and digital signaling is used for time division and asynchronous time division multiplexing. Let us see the frequency division multiplexing technique in details. What we do, first divide the available bandwidth into a single physical medium into a number of smaller independent frequency channels. So, the available bandwidth is divided into a number of smaller independent frequency channels. So, that is the first thing that is done. Then using modulation, independent message signals are translated into different frequency bands. As you have done, as you have seen, by using modulation this can be done. That means, independent message signals can be translated into different frequency bands. Then third thing that is done is, as all the modulated signals are combined into a linear summing circuit to form a composite signal for transmission through the medium which has higher bandwidth. Finally, the carriers are used to modulate the individual message signals. Okay, the carriers used to modulate the individual message signals are called subcarriers, as we shall see. So, here we are not using a single frequency carrier, but a number of frequency carriers, and as I mentioned, we can use one of the three different techniques: amplitude modulation, frequency modulation or phase modulation. One of the three techniques can be used to generate analog signal and to translate the individual frequencies to different frequency bands by using different carrier frequencies. On the other hand, if your data is digital in nature, then you can use ASK, FSK or PSK or a combination of ASK and PSK to generate analog signal, which is known as QAM. So, depending on whether your data is analog or digital, you will be using either amplitude modulation, frequency modulation or phase modulation if your data is analog in nature. On the other hand, if your data is digital in nature, then you will use ASK, FSK, PSK or QSK to convert to generate the analog signal, as we have discussed in detail in the previous lectures. So, the basic frequency division multiplexing operation is explained in this diagram. Here you have got source 1, source 2 and source n sources, 1 to n sources. Now, each of the frequency band of each of the signals is shown here. So, that means it is like this in the frequency domain. Now, as you do the modulation by using a frequency Fi, as we know, after amplitude modulation the bandwidth becomes like this around Fi. So, the bandwidth becomes double and the frequency of the carrier is Fi. That means, here is the frequency of the carrier is Fi. Now, we are modulating different signals with different frequencies. So, these are known as subcarriers F1, F2 and Fn. So, you can see here, if the bandwidth, transmitted bandwidth is from here to here, we can send all the signals F1, F2 and Fn, all signals can be transmitted through the medium. So, here after modulation we are combining and then sending through the transmission media. If it is air, then you do not have to do this, because all the signals will be sent through the air, and at the receiving end the separation can be done by suitable technique. As it is shown here, we are receiving the different signals F1, F2 up to Fn. So, these signals are received, and then with the help of demodulator they are separated out, and the demodulator then separates out each of these signals carriers F1, F2, Fn. So, here you get different frequency bands. So, say for example, here the carrier frequency F1 is filtered, here the carrier frequency F2 is filtered, here the carrier frequency Fn is filtered. So, they are filtered out, then they are sent to different destinations. And here it is shown in more details. So, the carrier frequencies Fc1, Fc2 and Fc3. Apart from having different bandwidths, separate bandwidths for each of these signals coming from different sources, some extra overhead is there, which is known as guard band. This guard band is necessary so that channels are separated by strips of unused bandwidth to prevent inter-channel crosstalk. If the channels are very close, then the signal of one channel will disturb the signal of other channel. Sometimes we observe that in whenever we receive radio signals, that adjacent channels are so close that if the filtering is not done properly, then it disturbs the signal of adjacent channels. So, that kind of thing can happen. So, to avoid that, we have to use guard bands between each of these bandwidths, as you can see, that is required for each of the signals. So, if you have to take care of not only the bandwidths of each of these subcarriers, but also the bandwidth of the guard bands together to decide the bandwidth of the channel. That means, the channel must have a bandwidth which is sum of the individual channel bandwidths plus the guard band bandwidths. And frequency division multiplexing has found applications in our day to day life. As you know, transmission of AM and FM radio is done by using this technique, and with the help of the radio receiver you can tune different channels. That means, you can select different frequencies and listen to that particular channel. So, AM and FM radio broadcasting it is used. Similarly, it is also used in TV broadcasting. In TV broadcasting also you can select different channels with the help of the tuner of your TV and watch different channels. And in cable television, same thing is done through a coaxial cable. As we know that each channel will require about 6 megahertz, and as we know a cable can provide you a bandwidth of about 500 megahertz. So, through a single coaxial cable that is being used for cable television, you can send as many as 100 different channels, and then you can separate out with the help of the receiver, tuners in the receiver, which are nothing but band pass filters. So, we see that analog transmission is necessary in all these cases, so that the signal has band pass nature, and then different frequency bands can be multiplexed multiplexed through the transmission media. And wavelength division multiplexing is commonly used in case of optical fiber, and particularly we have observed that optical fiber medium provides enormous bandwidth, and since it provides enormous bandwidth, and WDM is the most viable technology that overcomes the huge optoelectronic bandwidth mismatch. Here the mismatch is coming because the optical fiber has very high bandwidth. Individual users bandwidth requirement is much smaller. So, we have to send a large number of signals through the optical fiber, or we would like to the optical fiber bandwidth has to be shared by the signal of a large number of users. How that can be done? That can be done by using wavelength division multiplexing. It is somewhat similar to frequency division multiplexing, but at these higher frequencies normally we refer to frequency division multiplexing as wavelength division multiplexing, because wavelength value is smaller. So, wavelength division multiplexing optical fiber network comprises optical wavelength switches or routers interconnected by point to point fiber links. That means, there are switches and routers. That means, you have got say switch or router, and you have got optical fiber cable, and then this switch can receive a number of signals, and switch can also separate out a large number of signals. So, this is how it is being done, and this is your optical fiber cable. Now, end users may communicate with each other through all optical channels known as light paths, which may span over more than one fiber links. Here I have shown only one link, but you may not have only one link. In between there may be more switches, and as a consequence the optical signal, the light signal can pass through a number of switches in the optical domain, can reach the other side. So, this can happen whenever you have got optical switches, and this wavelength division multiplexing is becoming very popular, and the basic concept is shown here. Here again we have got different sources, and they are modulated with different carrier frequencies or wavelengths, as you can see. So, the bandwidth of, in terms of wavelength, a particular source say I is from W lambda 1 to lambda j. So, here for example, this is the signal coming from channel 1 lambda 1 to lambda 2, channel 2 lambda 3 to lambda 4. You can see there is some guard band in between. Then for channel n lambda 2n minus 1 to 2n. So, these different wavelengths can be multiplexed and sent through a optical fiber cable. So, this signal is going through an optical fiber cable, signals or optical signals of different wavelengths, and at the receiving end they can be separated out, and that filtering can be done, and we can get different frequencies, different wavelengths, as you can see here lambda I to lambda j meant for a particular channel. You may be asking how the filtering is done in optical domain. You may remember in your school days you have done experiment with prism. So, here as you can see the light coming out from the other side of the prism depends on the incidence angle and the wavelength. So, the lights can be made incident to this side with different angles, so that all of them come out with the same angle from the other side. Then it can be sent through optical fiber cable. At the other end again they can be separated out by using another prism. So, this is a very simple example which shows how wavelength division multiplexing can be done, how the different light signals can be combined and then can be sent through a single optical fiber, and again they can be separated out at the other end with the help of prism. So, somewhat similar devices can be used in practice in wavelength division multiplexing. Then coming to the digital one, that time division multiplexing, we have discussed the FDM and WDM, which uses analog signaling as you have seen, and now we shall consider time division multiplexing and two types, synchronous and asynchronous, which uses digital signaling. So, time division multiplexing is possible when the bandwidth of the medium exceeds the data rate of digital signals to be transmitted. So, here when the bandwidth of the medium exceeds the data rate of the signals to be transmitted. So, the possibility arises because of the same reason as frequency division multiplexing. However, it is done in a different way. Here what we can do, multiple digital signals can be carried on a single transmission path by interleaving portions of each signal in time. So, we shall interleave different signals one after the other and send through the medium. So, interleaving can be done at the bit level or in the blocks of bytes. It may be possible to do the interleaving at the bit level, say one bit of one signal, second bit another bit of another signal, and a third bit of another signal, and so on. It can be done, the interleaving can be done in this way, or interleaving can be done in terms of blocks of bytes. And of course, as we know, here we have to generate data in digital form, and you have to do suitable encoding like digital data to digital signal encoding, or if your data is analog in nature, then you have to convert into digital form by using pulse code modulation or delta modulation, get the digital signal, then you can do time division multiplexing. So, here what we do, the incoming data from each source are briefly buffered, and each buffer is typically 1 bit or 1 character in length. So, first the signal is received, then the signals are buffered before doing the multiplexing. Then the buffers are scanned sequentially to form a composite data stream. So, we can say that the scanning is done one after the other from different signals from the different buffers to form a composite signal. The scan operation is sufficiently rapid, so that each buffer is emptied before more data can arrive. So, here this is being explained, and another requirement is that composite data rate must be at least equal to the sum of the individual data rates. That means, the composite data rate that is being formed here, that one the that bandwidth of this must be, that data rate of this side should be more than the sum of the individual data rates. So, here what is done, some kind of framing, as you can see the interleaving is done, and here we have received coming from source 1 that a part of data from source 1 in time, here it is essentially time. Then the data from source 2, then data from source 3, in this way data from source n. So, these are scanned one after the other, then a frame is sent, then comes the next frame, again it is taken from another source, some 1 bit or more number of bits, then from channel 2 S2 source 2 1 bits or more number of bits, in this way it goes up to channel n, and again it is repeated. This is how it is done, scanning is done. Now, question arises, whenever you do the framing, say you are doing a frame some kind of framing, we are sending, say this is from source 1, this is from source 2, this is from source 3, in this way source n. Then of course, another stream is coming, this is one frame and this is another frame, source 1, source 2, and this is being sent. Now, question arises, how the other side, that is the receiving end, identifies that this is the beginning of a frame, and after the beginning of a frame is identified, then of course, the data from each of these sources can be taken out, provided they operate at the same frequency. So, here the requirement is that transmitter and receiver must operate at the same frequency, and moreover they should be able to identify the beginning of a frame. That is being done by using a separate channel, you can say. This channel is known as sync. Through this channel the sync characters are sent. So, at the beginning of each channel the sync character is sent, synchronization character is sent, and usually the synchronization character is say a sequence of 1 0 1 0. So, you may send 8 bits of 10 1010, that forms the synchronization character, and after this is detected at the receiving end, subsequent slots are for different data. So, this is considered a channel, say channel 1, this is again channel 1. So, in this way channel 1 is repeated. So, for the source S1 data is taken from the channel 1, then data is taken from channel 2, this is your channel 2 from source 2. It is predefined that data will be present in this time slot from source 1, in this time slot from source 2, and so on. Now, sometimes it so happens that the data rate is not matching which is coming from the source. For example, for the purpose of multiplexing, your requirement is say 8000 bits per second. On the other hand, from the source the data is coming at the rate of 7200 bits per second. So, data rates are different. In such a situation, what will you do? In such a case, a technique known as pulse stuffing is used, so that the synchronization of different data rates are possible. So, what is done? Some dummy bits are inserted to generate data rate of 8000 bits per second, then they are sent by the receiver, and at the receiving end the additional bits which are received are separated out to get back the original data, which has the data rate of 7200 bits per second. So, this is how pulse stuffing is done. Later on we shall take up an example to discuss it. So, here the synchronous time division multiplexing is shown. Here, as you can see, the data is coming from 4 sources. Here you have got A coming from source 1, B from source 2, C from source 3, and D from source 4. Now, as you can see, first frame has filled up all the slots A, B, C and D. That means, it is first it is taken from A, then it is taken from B, then it is taken from C and D. So, all the slots of first frame is filled up. However, so far as the second frame is concerned, that A, second B, second C is filled up, but there is no data in the fourth frame. So, this remains empty. So, and so far as the third frame is concerned, as you can see, you have got only 2 data A and B coming from source A and source B, and source C and source D has no data. So, these they remain empty. So, we find that in synchronous time division multiplexing, some of the slots may remain empty if the source has no data to send, as it has happened in this particular example. As you can see, in 4 frames, the first frame is filled up, second frame in the second frame 1 slot has remained empty, in the third frame 2 slots have remained empty, in the fourth slot and the fourth frame 3 slots have remained empty. So, this leads to inefficient utilization of the channel bandwidth or the medium bandwidth. How do you overcome it? This limitation is overcome by using a technique known as statistical time division multiplexing. It is also known as asynchronous time division multiplexing or intelligent time division multiplexing. So, wastage that happens in case of synchronous time division multiplexing, usually we refer to that synchronous time division multiplexing is referred to as TDM, time division multiplexing. Now, this problem is overcome in statistical or asynchronous or intelligent time division multiplexing. How? In statistical TDM, time slots are allocated dynamically on demand. That means, in the previous case we have seen each slot is pre-assigned for a particular source, but here it is not so. Here the slots are allocated dynamically on demand as and when required by different sources. So, and it takes advantage of the fact that not all the attached devices may be transmitting all the time. It is based on the observation that all the sources may not be transmitting all the time, and some sources, for example, whenever we talk through telephone, sometimes we keep quiet, sometimes we talk quickly, sometimes we talk slowly. This is quite common, and sometimes we keep silent, think something, then say. Somewhat similar situation exists, and this particular statistical behavior is exploited in asynchronous time division multiplexing, and this is explained in this particular example. Here what has been done, say data is coming from again from 4 different sources, and here the different time slots are shown. In the first time slots, as you can see, we have got data from channel source C and source A. So, that first data, this is your A1, this is your A1, this is your C1 are filled up in the first frame, and this slot remains empty, this slot also remains empty. That means 2 slots of frame 1 remains empty if it is synchronous TDM. Then in the next frame, as you can see, we have got 3 data. That means there is no data from source A, however, you have got data from source B, C and D. So, this is your B1, C2 and D1. So, these are filled up with this data. On the other hand, in the frame 3, as you can see, we have data from source B and source D. So, source slots allocated to source B and source D are filled up, the other slots remain empty. Similarly, in the fourth slot, as you can see, the slot A is filled up, slot corresponding to source A is filled up, slot corresponding to C is filled up. On the other hand, the other 2 slots remain empty. So, this is how it is sent in synchronous time division multiplexing, and this is the time required from here to here. So, this is the overall time required in synchronous TDM. Now, let us see how we can use asynchronous TDM where we need not really follow the same sequence. For example, any data coming from any source can be sent. For example, here we can send A1, C1, and then again we can send B1, C2, and as you can see here, the size of the frame is only, the frame has got only 2 slots. So, in frame 1 we have sent A1 and C1, in frame 2 we have sent B1 and C2. So, essentially the bandwidth requirement is less here. So, here the bandwidth requirement was corresponding to 4 time slots, but here you have got corresponding to 2 time slots. So, A1 C1, in frame 2 we shall send B1 C2, the way it is have B1 C2, then in the next time frame we shall sort D2, then A1, then D2, then A2 and finally, in the 5th frame we shall send C3. So, total time required is less than as it was in synchronous TDM, and as a consequence the bandwidth requirement for transmission of data through asynchronous TDM will be much less. But there is a problem in this case. Here, as you have seen, there is no fixed slot. A1 is coming here, then C1 has come here, then as you can see in the same slot we are sending B1 here, in the same slot we are sending D1 here, in the same slot we are sending D3, D2 here, in the same slot we are sending C3. So, we see here there is no pre-allocated slot for a particular source. How the other side will know that this data has come from source number S1. So, that is the problem. That problem has to be overcome by providing address information. So, since the data arrive from and are distributed to IO lines unpredictably, that means unpredictably or asynchronously, the address information is provided to assure proper delivery. So, that the data can be delivered to the proper destination at the other end. This leads to more overhead per slot. So, what we have to do, apart from data, we have to send the address. If there is only a single channel, we can send address and followed by data, variable length data. That means one source per frame. That means per frame we are sending one source. However, the most general case is that we can send several frames, several data from several sources per frame. For example, this is the what we can do for each data from for each source can have address field, length field and data field. So, there are 3 different fields for a corresponding to data received from a single source, and these are the overheads address and length, because the other side has to identify that the data corresponds to this address, and also the length field has to be known, so that we can identify the next slot. And to minimize the overhead for address, sometimes we use relative addressing rather than absolute addressing, depending on the number of sources. Suppose you have got 8 sources. So, if there are 8 sources, instead of providing the full address, 3 bits are sufficient. So, we can take the modulo of the address, I mean modulo of the number of sources. So, 3 bits will be left out, lower order 3 bits will be sufficient, and that can be used as address if we have got 8 sources. And similarly, length field, that instead of this we can say the number of bytes is 1, then 00, number of bytes is 2, then 02, like that can also be appended as part of the address field. So, in this way we can try to reduce the overhead, but whatever we do, there will be some overhead that is that cannot be escaped. So, there will be some overhead in asynchronous time division multiplexing, because you have to send the address information along with the data. However, it has got the advantage that it makes better utilization of the channel. And particularly in asynchronous time division multiplexing, the data rate at the output is less than the data rate at the inputs. That is the primary condition for asynchronous time division multiplexing. However, there are situations, there are peak periods where usually more data is generated than other times. So, in the peak period, that condition may be violated. That means, the incoming data rate may be more than the outgoing data rate possible. So, in such a case, only alternative is to use buffers of suitable size, and then the data can be temporarily stored before sending, and this problem of asynchronous time division multiplexing is overcome by use of buffers. And obviously, more the there is a trade off. It is a trade off between the buffer size and how much extra data can be stored, or what is the maximum data rate that can be supported. Maximum input data rate, output data rate is fixed. So, there is a trade off. Nowadays, cost of the memory devices has come down, and as a consequence it is better, it is more memories, it is you can afford to have more memory. On the other hand, the channel capacity is quite costly. So, this is usually overcome by having more and more memory. For example, Let us assume n is the number of inputs, r is the data rate of each source, m is equal to the effective capacity of the output. Obviously, m will be less than n into r, and alpha is the mean fraction of time each input is transmitting. That means, each source is not transmitting all the time. That is our basic premise, and obviously, alpha is varies from 0 to 1. Then a measure of the compression C is the ratio of the m, that is the effective capacity of the output, by NR, is obviously it will have value less than 1, but it will also have value in between alpha and 1. So, we can see here this compression that is possible. That means, we can have lesser output bandwidth than the sum of the input bandwidths, and that ratio is C is equal to m by NR, and that can be achieved, and based on experiments you can decide what will be the value of m for a particular application. That will definitely depend on the value of alpha and also n and r. So, the performance of TDM synchronous time division multiplexing can be decided based on the statistical phenomenon, that means mean fraction of time each input is transmitting, based on that, and also we can add buffers to improve the performance. I think our discussion on multiplexing will not be complete if we do not discuss about another very important technique, which is known as inverse multiplexing. We have seen that multiplexing is used when the bandwidth of the channel is more than the bandwidth of the input sources, but here we are performing something different. Suppose an organization is sending voice, video and data through the same medium, multimedia signal. Now, voice bandwidth requirement can be 64 kilobits per second, video bandwidth typical requirement is 1.54 megabits per second, and data bandwidth can be say 128 kilobits per second. This is the requirement, but you do not usually send video all the time. Sometimes you are sending voice, several voice signals, several data signals. Sometimes you are doing video conferencing, sending video signals. So, at different instance of time your requirement is different. One possibility to satisfy your requirement is you can use a link, you can have a lease line with capacity of 1.54 megabits per second. So, you can send data, and whenever you are sending voice or video, you will be sending through this particular channel. Obviously, you will not be utilizing the full capacity of the leased line or the medium that we have acquired. What an organization can do in such a case, they can have that bandwidth on demand. So, what they can do? They can have several say 128 kilobits channel available, and that number can be made available depending on the requirement. So, the bandwidth required can be available in terms of say 128 into n. That value of n is decided by the requirement at a particular instant. So, what we are doing, that input data is multiplexed, demultiplexed, then multiplexed at the other end to generate video. That means, several channels, the video data can be sent through several channels, and at the other end they can be combined and to generate the video data. So, this particular concept is becoming more popular for proper utilization of the channel bandwidth and also for cost effectiveness. So, these are the various techniques of multiplexing we have discussed. Now, it is time to give you some review questions. First question is, in what situation multiplexing is used? Second question is, distinguish between the two basic multiplexing techniques. Third question is, why guard bands are used in frequency division multiplexing? Fourth question is, why sync pulse is required in time division multiplexing? Fifth question is, what limitation of TDM is overcome in asynchronous time division multiplexing and how? Fifth question is, design a time division multiplexing system having output bandwidth of 256 kilobits per second to send data from 4 analog sources of 2 kilohertz bandwidth and 8 digital signals of 7200 bits per second. So, here you will design a time division multiplexing system by making use of pulse stuffing and other techniques. And these answer to these questions will be given in the next lecture. And here are the answer to the questions of lecture number 10. First question was, which modulation technique is used in optical communication? As I mentioned in the previous lecture, that on off keying is used in optical communication. We are sending light signal or not, I mean whenever it is 1 and whenever it is 0, you are not sending any light signal. That is why it is called on off keying, and this is being used in optical communication. Second question was, what are the 3 modulation techniques possible in modems? The 3 modulation techniques possible in modems are amplitude shift keying, frequency shift keying and phase shift keying, or a combination known as QAM. Later on we shall discuss about modem in more details, and we shall see in different standards how these modulation techniques are used. So, there are it is not really 3, we can say it is 4. However, the QAM can be considered as a combination of ASK and PSK. The third question was, why PSK is preferred as the modulation technique in modems? In PSK scheme, it is possible to send signal having more than one digital value. The approach is known as quadrature PSK. That means, here the baud rate is more than the data rate. That means, you can achieve higher data rate by using the QPSK, and we have already discussed about it. That is why PSK is preferred in modems. Fourth question was, out of the 3 digital to analog modulation techniques, which one provides higher data rate? For a given transmission bandwidth, higher data rate can be achieved in case of PSK. In other words, in PSK higher channel capacity is achieved, although the signaling rate is lower. So, that is all in this lecture. In the next lecture, we shall discuss about some applications of multiplexing techniques like telephone system and other things. Thank you.